Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II, Module 27. Today, Nagata Smyrnov Metrization theorem. As mentioned earlier, Urysohn's metrization theorem does not give a complete answer to metrizability. This problem was solved by efforts of several people. There are various versions of metrizability theorem. We shall now concentrate on one such result which seems to be most satisfactory, namely Nagata Smyrnov metrization theorem. We shall present a proof due to Nagata. A proof due to Smyrnov, you may look into Willard's book. Before that, we need to introduce another version of normality. So, the Nagata's proof of metrization theorem is in spirit similar to Urysohn's, but since second countability is removed now, the embedding will be in a much larger product space, and also we need a little more strengthening than normality. So that is what we want to introduce now. A topological space X is said to be perfectly normal if for every pair AB of disjoint closed sets inside X, there exists a map H from X to -1 plus 1 such that A is the precise inverse image of -1 and B is the precise inverse image of 1. Okay. Alright. So I have said AB disjoint closed subsets. If one of them is empty, it doesn't make sense. So both of them should be non-empty also. So that is necessary. Alright. That is assumed when you are talking about normality and so on. The precise inverse image is stronger thing. So even in a normal space, you will have A going to -1 and B going to 1. That is possible, but there is more points may go to -1 and more points may go to +1. So that is where the perfect normality comes. This precise set of points wherein this A is precise set of points wherein H takes value -1. Similarly, B is precise set of points wherein H takes value +1. Okay. A normal space is perfectly normal if and only if each closed subset is G delta. So this is where the link between perfectly normal and normal is established. G delta is the key. Remember that under a continuous function, inverse image of any singleton, continuous function into a metric space, okay, into a R for example, inverse image of a singleton under a continuous function is a G delta. Okay, so if it is perfectly normal, A and B will be G delta sets, right? So what it says is each closed subset is G delta. Clearly, perfectly normal is normal, there is no problem. So proving G delta for every closed set of G delta is what you have to show. That is all we want to say. So if only if part is obvious, because once you have this, closed subsets must be G delta. Okay. If and only if is what I want to show. Right. So to prove the if part, suppose A is intersection of UNs and B is intersection of VNs for all UN and VN. Okay, UN and VN are all open subsets for all n, and A intersection B is empty. Start with A and B are empty subsets. Okay, and write A as intersection of UN because it's G delta, B is intersection of UN, G delta. Both UN and VN for all of n, they are open subsets. By normality, we can first show, first of all assume that UN intersection VM is empty. Okay, so you have A is contained inside UN, B is contained inside VM, but they may not be disjoint. Okay, A and B are closed subsets, disjoint closed subsets. Therefore, inside these open subsets, you can choose smaller open subsets such that UM intersection VM is 1. Okay, but A will contain A. So if we make some, if you replace some UN by some UN prime, which still contains A and a smaller, then this property will still be true. So one by one you can replace UN and VN such that UN intersection VM is empty for all n and m inside M. Next, we can also assume that UN is contained inside UN plus 1 bar contained inside UN plus 1 for all n. Okay, once you have these UNs, okay, you can make it U1 intersection U2, that will be open subset. U1 intersection U2 intersection U3 will be open subset. Inside open subsets, you can choose a smaller one such that UN plus 1 bar is contained inside that, and so on. So you can make it decreasing. Similarly, you can make VNs also decreasing. So that is what you can do by rearranging this, redefining these UNs. Now let Fn from x to 0, 1 be such that Fn of x minus Un is singleton 1 and Fn of Un plus 1 bar is 0. So this is by normality. I am not saying this is precise set. This closed set going to 1 and this complement is going to 0, because this UN, x minus UN is larger, x minus UN does not intersect UN plus 1 bar, UN plus 1 bar, and this were disjoint subsets. So you have got a sequence of functions with this property. Take f to be, sum of these fn's. Only thing is you should divide by some factor so that the whole thing is convergent. So I am dividing by 2 power n. Because I know that these fn's are bounded by 1, so this will be less than equal to 1 by 2 power n summation, so this will be also convergent. Okay, so this dividing by some numbers is a general principle which you have to learn in analysis. Okay, sometimes this may not be 2 power anything. If you have sequence of points, positive, non-negative things, you can always divide them by some larger sequence of another sequence which is convergent, so that you can make this one is convergent. It then follows that f from x to 0, 1 is continuous, because each fn divided by 2 power n is continuous. Okay, so this is uniformly convergent because 1 is dominated by 1 by 2 power n. Okay, so uniform limit, therefore f is continuous, and hence now what happens? A is precise inverse of 0 of this one, because if x belongs to A, it must be inside every UN, right? X is inside, it is A belongs to, x belongs to A means x is inside every UN, right? So there is no question for every UN. You see, this whole thing is 0, means corresponding Fn is 0. Therefore, you see the precise 0 set. Okay. Similarly, we can construct a continuous function g from x to 0, 1 such that b is precisely g inverse of 0. All that you have to do is same construction, do it with Vn's, that's all. Okay. So you have two different functions. I want a single function to do that job. So this function f is such that its inverse image of 0, inverse image 0 is A, G such a inverse image 0 is B. Now I want one single function such that inverse image under that is 0, inverse image of 0 is or minus 1 is A, and plus 1 is B, the other way around. So for that I just take h equal to f minus g to f plus g. See, f plus g makes sense because sum is never 0. See, if f is 0, both of them are positive first of all, non-negative. If f is 0, that must be inside A, okay, which is disjoint from B, right? Outside B, outside A it is not 0. And outside B, G is not 0. So A and B are disjoint, therefore f plus g is never 0. So I can divide by f plus g. F minus g divided by f plus g is always takes values between 0 and 1 is what I have to. So minus 1 to plus 1. Modulus of this one is less than or equal to 1 because this is always smaller than this one, that's all. Modulus of this is less than or equal to 1. So this h takes values with minus 1 plus 1. Okay. Finally, suppose this h of x is 1. What does that mean? These two are equal. F minus g equal to f plus g equal to this divided this one equal to 1, but these two are equal. What does that mean? F minus g equal to f plus g, right? What does that mean? So such points are precisely g must be 0, right? So that will be a point of g. Similarly, f minus g equal to f plus g equal to 0 means f equal to g, right? Sorry, suppose this is minus 1. This minus 1 means f minus g equal to minus f plus g. So that f must be 0, right? So h inverse of minus 1 is precisely A and h inverse of 1 is precisely B. All right. So this is perfect normality given by normality plus every closed subset being G delta. Now let us come to Nagata Smyrnov Metrization theorem proof, which will be much simpler now because we have perfect normality here. A T3 space is metrizable. See, there is no second countability now, right? If and only it has a sigma locally finite basis. Sigma locally finite basis should ring a bell. That is something to do with paracompactness. Okay. So proof of the only if part. Okay. If and only if is there, only if it has sigma locally finite basis. So that all that you have to do is a metrizable space has sigma locally finite basis. Okay, this is what we have to prove. It actually is a metric space. We have seen that it is paracompact. So for each n belonging to n, let un be a locally finite open refinement of the open cover B1 by nx, x belonging to x. Fix n. Take B1 by nx as x range over x. This is a cover. Okay. This is an open cover for each n. So that take un to be a locally finite open refinement of this one. So for each n I have got a locally finite open refinement. Okay. All that I want to do is now, if you take union of all these uns, call that as B, this is a base for the topology on X. Okay, this I am leaving it as exercise because we have done so much of this kind of things. Okay, so for all n is involved, that is all you have to use. All right. So show that this B is a base now. Clearly, this is sigma locally finite because by definition each Now by choice UNs are locally finite, so by definition this is sigma locally finite. Okay, let us now prove the if part. Let X tau be a T3 space and B equal to union of these Bn's be a base for tau. Okay. Remember, each base is also a cover for X, open cover. Where each Bn, I am again writing down it indexing with Bn alpha, where alpha is in lambda n. So Bn's are members of Bn's are indexed by this set lambda n. Okay, and each Bn is locally finite family. This is the starting hypothesis now. Now take lambda to be the union of all these lambda n's over n. Okay, so this lambda is going to be our indexing set for, your last time we took I raised to this n natural numbers. Now I would like to take I raised to lambda, but I will do a slightly better job here. Namely, the proof is now going to be similar to the proof of Smyrnov metrization theorem, in the sense that we are going to produce an embedding of X inside the Hilbert space L2 lambda, the L2 space. Okay, with L2 norm. So I will recall what is this L2 of lambda on any set. Okay, any set L2 of that makes sense. Okay, that is what I am going to do now. I am just recalling this, the generalized Hilbert space. Okay, for any function f from lambda to r, let us denote SF. SF you can read it at support of f to be all those lambda such that f lambda is not 0. Okay. Take L2 of lambda, collection of all functions from lambda to r, okay, such that SF is countable. And when it is countable, look at the sum of all the f lambda squares. Sum total of that is definite. So it is square summable functions. That is the terminology. Okay, square summable functions form a Hilbert space. Okay, I will just use the word Hilbert space because the inner product here is not being exactly used, only the norm is used. And what is the norm? Norm is square root of summation of f alpha square. Okay, if you want to know what is the inner product, it is nothing but fg inner product is summation f alpha g alpha. If you have complex valued functions, you take summation f alpha g alpha bar and so on. We are not interested in that part. We are just interested in this norm. Okay, so this is the Hilbert space. The first step is, since every open cover has a refinement consisting of members of B, because B is a base, right? Every open cover, for each point you can select a member of the B contained inside that will be refinement. So, but B is locally finite. Therefore, from 3.6 follows that X is paracompact. Okay, so that is the link between the condition sigma locally finite base and this one. In particular, X is normal. What we want? We want perfect normality here. We will see why. So first we have seen that it is normal space. Second space is, we shall now prove that every open set U in X is F sigma. So now you see G delta and F sigmas are all both coming together here. F sigma means what? Union of countably many closed subsets, right? every open subset in X is F sigma. Okay, then from theorem 6.7 it follows that Fx is perfectly normal. Okay, you want to recall theorem 382. Normal space is perfectly normal if you know if every closed subset is a G delta. You take the complements, right? That's all. Okay. So it's perfectly normality is there. Next, by regularity given X belonging to U, there exists a basic element B, which you may call it as B lambda x inside X, such that X is contained inside B, contained inside B bar, contained inside U. It follows that if you put Bn equal to union of all these B lambda x bars, okay, closures of all that, as lambda reigns over lambda n, the union of closures of all locally finite this is a locally finite family, and hence is a closed subset. Okay, because this is locally finite. B curly B was sigma locally finite. Each B lambda Bn's were curly Bn's were locally finite, and I am taking these things are inside B lambdas, okay, lambda n's, sorry, here. Therefore, this is locally finite and hence Bn's are closed. Also note that Bn is contained inside U because B lambdas, all of them B lambda bars are contained inside U. Therefore, we have U itself is union of all these Bn's. For each point there is something. When you take the whole of them, it has to cover U itself. So what we have shown, U is countable union of closed subsets. Okay, so that completes the proof that every open subset is F sigma. Third step is take each B lambda inside this base. By step 2, we have a continuous function F lambda from X to I such that B lambda is precise non-zero points. All lambda all x such that F lambda of X is not equal to 0. Okay, the B lambdas are open subsets. Every complement is a closed subset. That will be a precise set of 0, so it is not 0, that's all. For each n inside n, define Gn from x to 0 infinity. We are constructing these functions so that finally we can take all of them and put them inside the Hilbert space, generalize the Hilbert space. So define Gn to be from x from 1 to infinity by the formula Gn of x is, this adding one is just for carefulness, okay. You could have added any epsilon, no problem. 1 plus F lambda x square, where lambda ranges over lambda n. So this is a countable family now. Okay, this square summable. So this makes sense. So 1 plus that makes sense, square root makes sense. So that is Gn of x. By the local finiteness of the family, number of Bn's here, okay, this is actually finite now. Finite sum. It follows that Gn is well defined. For the same reason, it is continuous also because it is a finite sum. This is continuous. 1 plus that is continuous. And it is never 0. That is why I have put 1 here or some epsilon here. I can take the square root. The square root is also continuous. Note that for each lambda inside lambda, there is a unique n lambda inside n such that lambda is in lambda n lambda. Why? Look at this definition of our capital lambda. This is a disjoint union. Okay, each lambda here belongs to exactly one of the lambda ends. That's all I am using. So that is important here, to take the indexing set disjoint union of those countable disjoint union of arbitrary families, whatever. Okay, so where were we? So each lambda belongs to unique n lambda. Okay, so I can talk about when lambda is in n lambda, I can take h lambda of x to be f lambda of x divided by this number n lambda is some. Okay, n lambda is some integer, positive integer. G n lambda also makes sense. Okay, corresponding n lambda. For each lambda, it is a unique n lambda here. Okay, G n lambda of x. So divide by this one. This is a non-zero function. So divide by that. So f lambda is continuous. This is continuous. H lambdas are continuous. Okay, are all these continuous functions taking values inside I now, because f lambda is only one of, you see, if you take the square of this square, then this function is one of them here. So the numerator is always smaller than denominator, and they are all positive. So they take values inside I. Okay, now I can define h from x to I raised to lambda itself. Okay, in particular it will be inside r raised to lambda, no problem, by the formula hx of lambda equal to h lambda of x. Hx is a function from lambda to I, so its lambdath value, you can think of the function or you can think of it as an element in the product, so it's lambdath coordinate, either way it is h lambda of x. By the very definition, if you take the product topology, it would be continuous. Okay, the very first thing to do is check that h lambda is, first of all, you have defined it as an element of r raised to lambda, but I want it to be inside L2 of lambda. L2 of lambda is a subspace of r raised to lambda. This is an element of r raised to lambda. So this follows easily, since first of all, for each fixed x, hx of lambda is not equal to 0. For finitely many lambda is inside lambda n, for each lambda n is finite, therefore set of points where hx lambda is not equal to 0 is countable. So S of hx is the set of points wherein it is not 0, this is support, that is countable. Now second thing is, if you take the sum of all of them after squaring the square and then take the sum, the finite only on fixing lambda n, this is a finite sum, that is nothing but summation h lambda of x square, lambda inside lambda n. Okay, but by definition this is f lambda x square divided by n square, because I have to take n lambda, but lambda is in lambda n, this n is this n itself here, n square gn of x square. I don't have to write gn lambda, because n lambdas are all n here, because lambda is in lambda n. Okay, and this summation, this number is 1 plus this summation, so this is smaller than this one, so this is less than 1 by n square. If for each n this is less than 1 by n square, when you take summation of all of them, that will be less than summation of 1 by n square, which is convergent, and we wanted that one to be convergent. Therefore hx is an element of L2. So we have got a function x to L2. All right.
Sir, may you please repeat this step? So we had from starting with every element of x, we wanted to associate a element of L2 of lambda. So that was from step 2. We found that every b lambda was open set, so we can associate a function so that it is exactly non-zero. That was the first step, first part of step.
That will come now in the proof of injectivity and continuity and all that. Right now, that this is open subset, precisely it is zero, etc. is not used. Only local finiteness is used, so that we have come, this is countable. The set of points S of H lambda.
Well defined,
right? So to show that it is inside L2 of lambda, only
divided by n lambda.
Right. This n lambda term is brought precisely for that. Not only that, why in the definition of Gn I have put 1 here? For two different purposes. First of all, I should be sure that when I take square roots, continuity, etc., I should not be getting into 0. Don't bump into 0. Secondly, this term is bigger than just this sum. So there are two purposes here. Okay, so Gnx is defined like this. I have told you any positive constant would have done the job here. Okay, so look at here now. These are inside I is not very crucial, but this numerator divided by this whole thing is less than n lambda. That is important. Okay, not just in I. That won't give you anything. It's less than 1 by n lambda. 1 divided by n lambda. That is important here. Okay, so that will be when you fix lambda inside n, lambda capital N, capital lambda n. What is n lambda? N lambda is n. So that same n is there. So whole thing finite. This finite collection is 1 by n square. Now you take the sum over n. So that must be convergent. That is convergent. So you are inside L2. Okay. Now comes, you see, the role of all these open subsets, etc. still will be there. Still you have to do that. Now check this H is injective. Given x1 not equal to x2 in X, okay, since X is Hausdorff space, is T3 space, that we have assumed, right? You will have B lambda, it's a basic element, such that x1 is in B lambda and x2 is not in B lambda. Right? So this immediately implies that the corresponding f lambda of x1 is not 0, but f lambda of x2 is 0. So precise zeros have been used here now for f lambdas. But h lambda of x1 is not 0, whereas h lambda of x2 is not 0, because what is h lambda? H lambda has f lambdas in the numerator, and this is always non-zero. This is 0 if and only if this is 0, right? That's what it is. So h lambda separate points. Okay, therefore hx1 of lambda will not be equal to hx2 of lambda. So this lambda coordinates will be different as soon as x1 is not equal to x2. Okay. So this proves H is injective. All right. See, countable family won't have been able to do. This is the local base we have used. Countable family of local base was possible if x were second countable. Okay. However, some countability was necessary. What is that? Sigma locally finiteness. So that plays the role here. Next, okay, to get L2. Otherwise, we won't be able to get L2. Next, we check that h from x to hx is a closed function. Okay. Injective, closed, continuity. These three things we have to show, right? So continuity is at the last. Okay. Let A be any closed subset of X. You have to show that HA is closed. Take phi outside of HA. It is inside HX, of course. Okay, everything is inside HX. In the whole L2, we don't know. We don't need that. Okay, to show something is embedding, you have to take the only image and work inside the image. So phi is h of some x for x inside x minus a because it is not in HA. But then x belongs to b lambda contained inside x minus a. Okay, a is starting with a closed subset. So you will have some b lambda such that x belongs to b lambda contained inside x minus a for some lambda. So that automatically implies h lambda of x is not 0. Whereas h lambda of a will be 0 for all a inside a. Okay. The precise set of non-zero elements are inside b lambda. So outside x minus a, outside a, so for all a, outside this inside x minus outside x minus a, for all a it will be 0. Therefore, if you take the norm of hx minus ha, okay, this is summation h lambda, no, is right, of this minus h of that one. There will be one term, it's okay, norm square is the summation squares and so on. When you are taking square root, there will be one term which is h lambda of x minus h lambda of a. There will be many other terms, they are all non-negative terms. This sum, therefore this thing is bigger than or equal to this one. Okay. In one coordinate, this is 0 and this is not 0. Okay. So hx minus h lambda modulus is precisely equal to h lambda of x, and that is positive. This happens for all a. One single number positive, and this norm is bigger than that for all a. That means the distance between hx and the set A is positive. Okay. Therefore, hx cannot be in the closure of HA bar, the HA bar closure. Distance between hx and h of A is positive. Okay. This says pointwise, but this is true for all a. Therefore, distance between hx and h capital A is positive. That means hx is not in the closure of HA. Okay, we want to show that HA is closed. So first of all, hx is not in the closure. Since this is true for all points x minus a, hx minus HA, this implies that hx minus HA itself is contained inside HA minus HA bar. Because if you take any point here, it's just now we have shown that it's not in HA bar, that's all. But by De Morgan law, this just means that HA bar is contained inside HA. If the bar is contained inside the set itself, that means that that set is closed. Okay. Maybe you can directly prove that from here to here it is an open set. I think proving closeness is easier, that's all. All right. Now let us check H is continuous. Okay. Now you see the full force of all these things will be used. How we have constructed. Given x belonging to x, choose epsilon, let epsilon be positive, we have to produce some open subset U around x such that x belongs to, x prime belongs to U implies norm of hx prime minus hx is less than epsilon. So this is the continuity. I am using the norm on the codomain. Okay. X is just a topological space, so I have to use only open subsets around that one, which has this. For every x, for every epsilon, I have to prove this. As soon as epsilon is given, choose some n such that n to infinity, I can put it a k also, earlier I had to k, so you have capital, no problem. N plus 1 to infinity 1 by n square is less than epsilon by 4. Maybe epsilon by 8 if you want, you can choose, no matter. Okay. By local finiteness of all these bn's, we get an open set V around X such that this open set V meets only finitely many members of Bn for all n less than or equal to capital N. For each of them you will get, say, B1 you will get V1, B2 you will get V2, up to B capital N you get V capital N, but then you can take the intersection of V1, V2, V capital N, call that as V. That's all. Okay, this V is a neighborhood of X which will make finitely many members of Bn, n ranging from 1 to capital N. Alright. Let us denote these members by B lambda I. So B lambda i's belong to all, they will all belong to B1, B2, B3 or B up to n, where I don't care. So totally they are in number k, finite. Now choose a neighborhood U of X such that U is inside this V, smaller neighborhood I am going to choose, and these finitely many continuous functions, no, h lambda I of x prime minus h lambda I of x is less than the sum epsilon I have chosen carefully, the sum epsilon. For this epsilon square root of epsilon by square root of 2k, choose neighborhoods. Okay, for each of them choose neighborhoods and then take the intersection. Take intersection with V, you will get a subset U contained inside U for which all these inequalities will be true for all points x prime inside U. Okay, that's by continuity of each h lambda i's. Finitely many of them you can do. So this yields for all x inside U. If you now take the summation n ranging to 1 to n and all points lambda inside lambda n, h modulus of hx lambda minus h lambda of x square, square if I take here, that will be epsilon divided by 2k. How many are there? K of them. So it's k times epsilon divided by 2k. Okay, and that is nothing but epsilon by 2. All right, all the sums up to capital N here, this is epsilon by 2. Okay, now on the other hand, what happens in the second part, namely n plus 1 to infinity. N plus 1 to infinity, take summation lambda inside capital lambda n, this is a double summation, hx, h lambda of x prime minus h lambda of x square. Okay, what happens to this summation? This is n to infinity as it is, lambda as it is, h lambda of x prime square plus h lambda of x square. Okay, so squares of difference is less than or equal to square of each individual term. So that is a very rough estimate actually, but that is enough because this summation, these are positive things. Okay, though this is maybe infinite, when lambda equal to lambda n, this is a finite sum actually. Okay, never mind, we can separate them out. If you take the first summation, it's n going 1 to infinity, this will be less than 1 by n square by choice. This is also less than 1 by n square. For each x prime x's, this is the property that we have chosen. Okay, so that is twice summation n plus 1 to infinity 1 by n square. Each of them is less than epsilon by 4. So twice that is less than epsilon by 2. Okay, thus it follows that U is the required neighborhood of x. So guess, if you take sum together, this sum square is less than epsilon by 2 plus this sum sort of square is less than epsilon. So we have to, instead of showing epsilon square, we have shown, doesn't matter. We should have square root of epsilon started with. Okay, so this proves the continuity of H, and thereby the theorem is proved. Okay, so here are a few exercises for you. One exercise here, which is not very difficult at all. Every metric space has a sigma locally finite base. Okay, I have put already as exercise, and I have put it as separately. In the proof somewhere, I should prove this one as an exercise, remember? So I have separately mentioned it, that's all. Maybe in the earlier theorem, never mind. So there are many problems in metrizations, like you may talk about when can a topological space be given a metric which is complete. Such things are called complete metrization. We shall not be able to discuss such things which are too special. Okay, thank you.